Module 24, Lecture B, Factor Components. By the end of this lecture, you will be able to apply dictionary learning, sparse coding, factor analysis, ICA, and NMF methods. Use mini-batch and topic modeling decompositions for larger or text-like data. And interpret components, scores, and reconstruction quality. Dictionary methods. Dictionary learning. Dictionary learning represents data as combinations of learned patterns called atoms, rather than using a fixed, predefined basis. It discovers recurring structures directly from the data, and each data point is reconstructed by weighting the atoms that best describe it. The aim is to build a compact, meaningful dictionary that can accurately represent the original data, making the method useful in areas such as image analysis, audio processing, and sensor data interpretation. In dictionary learning, sparsity means each observation is described using only a few dictionary atoms. This makes the representation easier to interpret and more robust, because it focuses on the most relevant patterns. By selecting only key components, sparse representations support tasks such as denoising, compression, feature extraction, and anomaly detection. In dictionary learning, evaluate both the learned atoms and the coefficients for each observation. Atoms capture recurring structures, while coefficients show how those structures reconstruct individual samples. A good dictionary should reduce reconstruction error while remaining stable and interpretable. Its size and sparsity must be balanced, since too few atoms or too much sparsity can miss important patterns, while too many atoms or weak sparsity can capture noise or make the decomposition unclear. Python code. Dictionary learning. Dictionary learning finds atoms from simple synthetic signals. Sparse codes represent each signal using only a few atoms, and reconstruction error measures how well those atoms combine to reproduce the original signal. The script imports the main tools needed for dictionary learning and visualization. NumPy supports efficient numerical array operations. Matplotlib is used to plot results, and Scikit-Learn provides the dictionary learning method for finding sparse basis representations of data. The full Scikit-Learn library is also imported, so its version information can be checked later. To create repeatable signals, we first set the random number generator to a fixed seed of 42. Then we make 40 evenly spaced values from 0 to 1 to use as the signal's x-axis. We define 3 basic atoms to build synthetic signals: a smooth sine wave, a rectangular pulse that is active over a limited range, and a sharply peaked exponential decay centered near the end of the x-axis. Together, these simple shapes provide the core building blocks for creating more complex signal patterns. Three arrays are stacked vertically to form the hidden atoms used in the model. Each atom is then normalized by dividing it by its own row norm, giving every atom unit length. This keeps their scales consistent, which supports the dictionary learning process. Random coefficients are generated as a 90x3 matrix with values between 0 and 1.5, representing possible contributions from hidden atoms to the signals. A random Boolean mask of the same size then selects about 45% of the entries to remain active. Multiplying the coefficients by this mask sets the rest to 0, creating a sparse signal representation. The code creates synthetic signals by combining coefficient values with the true underlying atoms. It then adds small random noise from a zero mean normal distribution to make the signals more realistic. This helps the model learn from data that includes the kinds of imperfections found in real signals. Before fitting the model, the code verifies that the signals data has 90 rows and 40 columns, meaning 90 signals with 40 measurements each. If the shape is different, it raises an error, because the dictionary learning model needs this exact input structure. This check helps catch formatting problems before the model runs. This setup uses Scikit-Learn's dictionary learning model to find 3 reusable patterns, or atoms, in the data, and represent each signal with a sparse combination of them. A sparsity setting of 0.8 encourages the model to use fewer atoms, while up to 500 iterations gives the optimization time to converge. The lasso-Lars transform method is chosen to produce sparse representations efficiently, and a fixed random state ensures reproducible results. The model first converts each signal into a sparse code, using only the dictionary atoms needed to represent it. The learned atoms are then taken as the signal building blocks, and the signals are reconstructed from the sparse codes and these atoms. Comparing the reconstruction with the originals shows how well the dictionary learning process captured the signal structure. We evaluate the sparse representation using 2 measures. First, we estimate the average number of active atoms in each signal by counting sparse code values whose absolute size is above 0.05. Then, we measure reconstruction quality with the mean squared error, which averages the squared differences between the original and reconstructed signals. The output summarizes key checks for a dictionary learning model. It reports the Scikit-Learn version for reproducibility, confirms the signal data shape, shows the average number of active atoms per signal to indicate sparsity, and gives the mean squared reconstruction error to measure how accurately the signals were reconstructed. The code sets up a Matplotlib figure with subplots to display the learned atoms. Using a wide 8 by 4 inch layout makes the signal patterns easier to compare. This prepares a visual space for inspecting the reusable patterns found through dictionary learning. Each learned atom is plotted against the signal position on the x-axis. The plots are labeled by atom number, starting from 1, so each atom can be easily identified in the legend. The plot is titled to show that it visualizes learned atoms from dictionary learning. The x-axis marks signal position, while the y-axis shows each atom's value at those positions. A legend identifies the different atom lines, and the plot is displayed so the learned signal patterns can be inspected visually. This script shows dictionary learning on synthetic signals made from 3 hidden building blocks with added noise. A model set to learn 3 components tries to recover those reusable patterns. The results report how sparse the representations are through the average number of active atoms per signal, and how accurately the signals are reconstructed using mean squared error. The learned atoms are then visualized and should closely resemble the original building blocks. Mini-batch dictionary. Mini-batch dictionary methods make dictionary learning more practical for large or rapidly changing data by updating the dictionary using small groups of observations instead of the full dataset. This reduces memory demands and works well for data such as image collections or sensor streams. Each mini-batch provides partial information, and over time, the dictionary is refined to capture the main recurring patterns. Mini-batch dictionary learning updates the dictionary using small chunks of data, balancing speed with good, sparse representations. It helps find meaningful, selective patterns in large datasets, and can adapt as new data arrives. This makes it useful for changing environments, such as social media analysis or industrial monitoring. To interpret a mini-batch dictionary model, examine the learned components and the sparse codes. The components show recurring patterns, while the sparse codes indicate which patterns explain each observation and how strongly. A good model finds meaningful components, reconstructs the data well, and uses only a limited number of active components. Because batch order, size, and diversity can influence learning, the model's component meaning and stability should be evaluated carefully. Python code. Mini-batch dictionary. This demonstration uses mini-batch dictionary learning on small-digit images to learn reusable atoms from many image patches. It then compares sparse reconstructions with the original data to show how well the learned atoms capture the main structure of the images. This setup imports the main tools needed for a digit image reconstruction task. NumPy supports numerical array work, Matplotlib handles visualization, and Scikit-Learn provides the dataset, model, evaluation metric, and preprocessing tools. The digits dataset supplies sample images. Mini-batch dictionary learning learns compact patterns from the data. Mean squared error measures reconstruction quality. And min-max scaling normalizes pixel values between 0 and 1 for more consistent performance. We use Scikit-Learn's load digits function to access a built-in dataset of handwritten digit images for quick, offline experiments. From this dataset, we take the first 300 images as input for later processing and analysis. Each digit image is stored as an 8x8 pixel grid. Before modeling, the code verifies that each image is 8x8 pixels, matching the required input format. If the images have a different shape, it raises an error to stop the process. This validation helps prevent later failures when the model expects a fixed image size. The images are first flattened, so each one becomes a single row in a two-dimensional dataset, making them suitable for machine learning models. Their pixel values are then scaled to the range from 0 to 1, using a minimum-maximum scaling method, which normalizes the data for later analysis or modeling. We configure a mini-batch dictionary learning model to learn 16 compact basis patterns from the data. Sparsity is encouraged, so each image uses only a few atoms, and training is done in batches of 32 for efficiency. The model runs for up to 80 iterations, uses a fixed random seed for reproducible results, applies the lasso-Lars method for sparse transformations, and keeps training output silent. The code converts the scaled images into sparse codes using the learned dictionary, showing which dictionary components each image relies on. It then reconstructs the images by combining those components according to the sparse codes. This lets us judge how well the dictionary represents and approximates the original images. We evaluate the reconstruction by measuring the root mean squared error between the scaled images and their reconstructed versions. We also count the non-zero entries in each sparse code to see how many dictionary atoms each image uses. Averaging these counts shows the overall sparsity of the representation. The output summarizes key checks for the dictionary learning model. It reports the Scikit-Learn version for reproducibility, the number of learned dictionary atoms to show how many patterns were extracted, the average number of active atoms used per image, and the reconstruction error on scaled pixel data to indicate how closely the reconstructed images match the originals. To visualize the learned atoms, a 32 by 32 grid is created and filled with 16 small image patterns. Each atom is reshaped into an 8 by 8 image, then placed into its position in a 4 by 4 layout based on its index. The result is a single larger grid that displays all learned patterns together. This code creates a square plotting area and displays the learned dictionary atoms as a grayscale image grid. It adds a clear title and axis labels to describe the grid layout, then removes tick marks for a cleaner view. Finally, it renders the plot so the learned digit image patterns can be visually inspected. This script applies mini-batch dictionary learning to a small set of digit images. It scales and flattens the images, then learns 16 reusable patterns, or atoms, that can sparsely reconstruct them. It reports reconstruction quality using root mean squared error and the average number of active atoms per image. The learned atoms are then displayed as small image patterns to show the features the model found useful. Sparse coding. Sparse coding represents data by using only a small number of active elements from a larger dictionary. It captures the most relevant components of each observation, such as key patterns in an image or themes in a document. The result is a compact set of scores where most values are near zero, leaving only the important information emphasized. Sparse coding represents data efficiently by using only a small number of important components. This makes patterns easier to interpret, while reducing noise and unnecessary detail. Across areas like images, biomedical signals, and customer analytics, it helps reveal the main structures in the data with less complexity. Sparse coding works best when it balances accurate reconstruction with a compact representation. If the code is too sparse, important details may be lost. If it is not sparse enough, the result can be harder to interpret. Used well, sparse coding reduces dimensionality and reveals meaningful, parts-based structure in complex data, helping connect raw observations to higher-level insights. Python code, sparse coding. This example shows sparse coding using learned components. The goal is to represent data with only a few active dictionary atoms. Then compare how reconstruction quality changes as the code becomes more or less sparse. We import key Python libraries for building and evaluating a sparse coding model. NumPy supports numerical array operations. Matplotlib helps visualize results. And Scikit-Learn provides the handwritten digits dataset, dictionary learning tools, error measurement, and data scaling. The data is normalized, so reconstruction errors can be compared more reliably. We begin by loading Scikit-Learn's handwritten digits dataset, a small collection often used for demonstrations. From it, we select the first 300-digit images to use in the sparse coding example. Each image is flattened into a single row of pixel values, changing the dataset from a three-dimensional image format into a two-dimensional array. This prepares the data for machine learning methods that require each example to be represented as one row of features. Before comparing reconstruction errors, the image pixel values are scaled to a common range, usually from 0 to 1. A minimum-maximum scaler is applied to the flattened images, putting each feature on the same scale. This makes later error comparisons more accurate and consistent. Before processing, we verify that the scaled image data has the expected shape. 300 images, each represented by 64 pixel features. If the dimensions do not match, an error is raised to signal that the input data is not properly formatted. A dictionary learning model from Scikit-Learn is configured to find 16 patterns in the data. It uses the lasso-Large transform method to produce sparse image representations, with an alpha value of 0.15, controlling how many components are active. A fixed random state makes the results reproducible, and the iteration limit of 80 controls how long the model searches for the best dictionary. The model learns sparse codes from the scaled images by fitting to the data and transforming it into compact representations. The images are then reconstructed by combining these sparse codes with the learned dictionary components, producing approximations of the original scaled images. For each image, we count how many dictionary atoms are active by checking which sparse code coefficients are larger than a small threshold in absolute value. We then average these counts to estimate the typical number of active atoms per image. Reconstruction quality is measured using the mean squared error between the scaled original images and their reconstructions. The output reports key checks for a sparse coding model, the Scikit-Learn version for reproducibility, the number of learned dictionary atoms, the average number of active atoms used per image, and the mean squared reconstruction error. Together, these values show how sparse the image representation is and how well the model reconstructs the original images. A bar chart is used to visualize the sparse code for one-digit image. Each bar represents a dictionary atom, and its height shows how strongly that atom contributes to reconstructing the image. The plot includes a title and axis labels, making it easy to see that most coefficients are 0 or close to 0, which is the main idea behind sparse coding. This script applies sparse coding to handwritten digit images by scaling and flattening them, then learning a small dictionary of 16 components with a lasso-based sparse coding method. Each image is represented using only a few active dictionary atoms, and the images are reconstructed from these sparse codes. The script evaluates performance with the mean squared reconstruction error and reports how many atoms are active on average. It also visualizes one sparse code to show that most coefficients are 0, confirming the sparsity of the representation. Scalable factor models. Latent factor analysis. Latent factor analysis explains many observed variables by identifying a smaller number of hidden influences behind them. In large, noisy datasets, variables may move together because of shared causes that are not directly measured, such as student engagement behind attendance and quiz scores, or lifestyle behind retail purchases. Its goal is not only to reduce data complexity, but also to reveal why patterns and variation occur. Scalable latent factor models find hidden patterns in very large datasets by updating estimates gradually as new data arrives, rather than processing everything at once. This makes them useful for streaming data, large surveys, and massive text collections. In documents, they can identify broad themes like politics or technology, while allowing each document to contain those themes to different degrees. To interpret a latent factor model, look at what each factor represents and how strongly each observation reflects it. Factors are understood through the observed variables most associated with them, while scores show an observation's level on those factors. Because latent factors are inferred rather than directly observed, they should be treated as useful interpretations, not absolute truths. A good model balances clear meaning with accurate reconstruction of the data to support analysis and decisions. Python code, latent factor analysis. This example shows how factor analysis can uncover hidden influences in synthetic data. It estimates shared latent factors from observed measurements and compares the learned patterns with the true ones. We import the main tools needed for analysis: NumPy for efficient numerical work, Matplotlib for creating visualizations, and Scikit-Learn for machine learning tasks. From Scikit-Learn, we use factor analysis to uncover latent factors in the data, and a standard scaler to put features on the same scale. Together, these imports prepare the data for analysis, modeling, and visualization. A random number generator is created with NumPy and initialized using the seed value 42. Setting the seed makes the generated random numbers repeatable each time the code runs, which helps ensure reproducible results in simulations, experiments, and teaching examples. The setup defines a sample of 600 students and 3 hidden factors to uncover underlying influences. It also names 8 observed measurements, such as attendance, assignments, and exams, which serve as the variables shaped by those hidden factors. The true loadings matrix represents the hidden factor structure that factor analysis is meant to recover. Its rows correspond to observed measurements, its columns correspond to hidden factors, and each value shows how strongly a factor influences a measurement. This simulated matrix defines the underlying relationships in the data. We simulate observed data by first generating hidden factor scores for each student, then adding random noise to represent measurement error. These hidden scores are combined with the true loading patterns through matrix multiplication, and the noise is added afterward. The result is data that reflects both underlying latent factors and imperfect measurement, making it suitable for factor analysis. The code first verifies that the observed data has the expected shape, one row per student and one column per feature. If the dimensions do not match, it raises an error to stop the process. This early check helps ensure the data is correctly structured before modeling begins. Before factor analysis, the data is standardized, so all variables are on a comparable scale. Scikit-Learn's standard scaler removes each feature's mean and scales it to unit variance, and its fit and transform step does this in one operation. This helps ensure that every feature contributes fairly, rather than letting variables with larger scales dominate the analysis. A factor analysis model is created with 3 factors and a fixed random state for reproducibility. The model is fit to the scaled data to extract factor scores, which represent the hidden patterns found in the measurements. The learned loadings are then obtained from the model components, showing how strongly each observed variable relates to each latent factor. We reconstruct the observed data by combining the learned factor scores with the model components and adding the model mean. This shows how well the latent factors reproduce the original data structure. We then compare the scaled observed data with the reconstruction using mean squared error, which measures the average squared difference and indicates how accurately the model preserves the data. The output reports key checks for the factor model, the Scikit-Learn version for reproducibility, the number of observed measurements to show the data's dimensionality, and the number of learned latent factors. It also gives the reconstruction mean squared error, rounded to 3 decimals, which indicates how well the learned factors recreate the scaled data. To interpret each learned factor, we identify the measurements with the strongest loadings. For every factor, we compare the absolute loading strengths, select the 3 largest, and match them to their feature names. Printing these top measurements with the factor number gives a concise description of what each factor represents. This code creates a heat map of the learned latent factor loadings using Matplotlib. It displays the loadings with a cool-warm color scale, labels the axes as latent factors and observed measurements, and names the factors F1, F2, and F3. The measurement labels identify the observed features, while the color bar shows the strength of each loading. The layout is adjusted for clarity, and the heat map is then displayed. This script uses factor analysis on synthetic student performance data to identify 3 hidden influences behind 8 measurements. It adds realistic noise, scales the data, and applies Scikit-Learn's factor analysis to estimate the latent structure. The output reports reconstruction error to show how well the model fits, highlights the measurements most linked to each factor, and uses a heat map to make the learned factor relationships easier to interpret. Independent component analysis. Independent component analysis, or ICA, is a technique for separating observed data into underlying independent sources. It assumes that complex measurements, such as sensor recordings, brain signals, documents, or financial data, are mixtures of hidden components. ICA helps uncover those components, such as isolating individual voices from mixed microphone recordings, or separating useful signals from noise. When applying ICA to large datasets, prioritize efficient computation, careful memory use, and pre-processing. Centering and whitening the data helps ICA focus on statistical independence rather than variance, which distinguishes it from principal component analysis. For very large or streaming data, use chunk-based or iterative processing, so the full dataset does not need to fit in memory. In text analysis, first convert text into numerical features, while considering whether ICA is appropriate for sparse non-negative data compared with methods such as non-negative matrix factorization. ICA components can be understood as hidden sources that influence the observed data, with weights showing how strongly each variable contributes and scores showing how present each source is in each sample. A component might represent a speaker in audio, or a neural rhythm or artifact in brain signals. The goal is not only to reconstruct the data well, but also to find components that are stable, computationally practical, and easy to interpret for tasks like artifact detection or data summarization. Python code, independent component analysis. This example uses independent component analysis to separate mixed signals and recover the hidden source patterns. It compares the original mixtures with the recovered sources to show how ICA reveals the underlying components. We import the main libraries needed for signal separation: NumPy for numerical array operations, Matplotlib for plotting signals, and Scikit-Learn for machine learning tools. From Scikit-Learn, fast ICA is used to separate mixed signals into independent components, while the standard scaler prepares the data by giving each feature a mean of 0 and a variance of 1, helping the ICA algorithm work effectively. We create 3 independent source signals for an independent component analysis example. A fixed, random seed makes the results reproducible, and the time range runs from 0 to 8 across 800 points. The sources are a smooth sine wave, a square wave that switches between -1 and 1, and a Laplace distributed signal with sharper peaks and heavier tails. The 3 source signals are first stacked into rows so they can be transformed together. A mixing matrix then defines how these sources combine to create the observed signals, with each row representing one mixture and each column representing one source. Multiplying the matrix by the stacked sources simulates the mixing process, producing signals that can later be separated with independent component analysis. The code verifies that the mixed signals data has the expected shape: 3 signals measured across all time points. If the structure is incorrect, it raises an error to stop the process. This check helps ensure the data is properly organized before further analysis. We standardize the mixed signals so each feature has a mean of 0 and a standard deviation of 1. Because the scaler expects features in columns, the signals are transposed before scaling. The result is a scaled set of observations prepared for independent component analysis. We use Scikit-Learn's fast ICA to extract 3 independent components from the scaled observations, with settings for reproducibility, convergence, and unit variance whitening. The sit and transform step separates the mixed signals into statistically independent sources. Then, the inverse transform step reconstructs the mixed signals from those sources, so they can be compared with the original observations. The reconstruction error is calculated to evaluate how well independent component analysis separated the signals, using the average squared difference between the original and reconstructed data. The Scikit-Learn version is printed for reproducibility, followed by the rounded mean squared reconstruction error to judge accuracy. Finally, the shape of the estimated sources is checked to confirm that the expected number of components was produced. This plot compares a mixed observed signal with the independent component recovered by independent component analysis. A Matplotlib figure is created. Both signals are drawn with partial transparency, and labels, a title, axis names, and a legend are added for clarity. Displaying the plot helps visually judge how well ICA separates the mixed signal into its underlying components. This script shows how independent component analysis can recover original signals from mixed observations. It creates 3 source signals, mixes them together, scales the mixtures, and then applies ICA to estimate the independent sources. A reconstruction error and a comparison plot are used to check performance, showing that ICA can effectively separate the mixed signals into their underlying components. Non-negative matrix factorization. Non-negative matrix factorization, or NMF, is used for data made of zero or positive values, such as word counts or pixel intensities. It represents each observation as a combination of non-negative components, which often makes the results easier to interpret. In text analysis, these components can capture themes like finance or sports, while each document is treated as a mix of those themes. Non-negative matrix factorization helps make large high-dimensional data easier to understand by reducing it to a smaller set of meaningful components, while preserving links to the original features. In text analysis, it can uncover topics from word patterns and show how strongly each document relates to them. In images and recommendations, it similarly finds useful building blocks, such as visual parts or preference patterns, that explain complex data in a simpler form. When scaling up non-negative matrix factorization, the goal is to balance meaningful interpretation with good reconstruction of the original data. The number of components should be large enough to capture important structure, but not so large that the results become hard to interpret or sensitive to noise. Mini-batch methods make this practical for large or streaming datasets by processing smaller chunks while still producing useful components for tasks such as search or clustering. Python code, non-negative matrix factorization. This example uses non-negative matrix factorization to identify topics in count data. The method finds additive components, and the results include the main words for each topic, along with the reconstruction error. This setup imports the main tools needed for text-based matrix factorization. NumPy supports efficient numerical work, while Scikit-Learn provides non-negative matrix factorization for decomposing text data into useful non-negative components. A count vectorizer turns documents into token count matrices, and mean squared error helps measure how well the model reconstructs the original data. The script begins with a small set of text documents grouped by topic. 2 documents focus on finance, 2 on politics, and 2 on sports, using representative words from each area. This compact dataset provides a simple basis for later topic analysis with non-negative matrix factorization. We use count vectorizer to convert text documents into a non-negative document term matrix, which is required for non-negative matrix factorization. Fitting the vectorizer learns the vocabulary and represents each document by the terms it contains. The extracted feature names are then stored, so the resulting topics can be interpreted by mapping them back to the original words. We create a non-negative matrix factorization model to extract 3 topics from the document term matrix. The model uses an initialization method that supports faster convergence, a fixed random state for reproducibility, and enough iterations to converge. After fitting, each document is represented as a mixture of the 3 topics, and the model components show how strongly each word contributes to each topic. To estimate how well the topic model represents the data, we reconstruct the document counts by combining each document's topic scores with the topic word patterns. We then compare this reconstruction with the original document term matrix using mean squared error. A lower error means the model has captured the data structure more accurately. The code reports key information about the modeling setup and results. It shows the Scikit-Learn version for compatibility, the document term matrix shape to indicate the number of documents and unique terms, and the mean squared reconstruction error to assess how well the non-negative matrix factorization model fits the data. A lower reconstruction error means the model recreates the original data more accurately. For each topic, we find the words with the strongest weights to make the topic easier to interpret. The process sorts the word weights, selects the top 4, retrieves the matching feature names, and prints them as a comma-separated label for that topic. This gives a concise view of the words most closely associated with each topic found by the non-negative matrix factorization model. The code takes the topic scores for the first document, rounds them to 2 decimal places for readability, and prints the result. This gives a simple view of how strongly that document relates to each identified topic. This script uses non-negative matrix factorization to find 3 hidden topics in a small collection of text documents. It identifies the most important words for each topic, helping reveal the main themes in the documents. It also measures how closely the model reconstructs the original document term data using mean-squared error, and shows the topic scores for the first document. Overall, it demonstrates how NMF can uncover meaningful patterns in text. Topic reconstruction. Mini-batch reconstruction. Mini-batch reconstruction evaluates how well a decomposition model captures patterns in large datasets by updating the model with small groups of data instead of processing everything at once. It uses learned components and their weights to approximate the original data, improving over time. The goal is not perfect reconstruction, but preserving the data's essential structure in a simpler form. When interpreting mini-batch reconstruction, connect the result to the components and scores that produced it. Components represent learned patterns, while scores show how strongly each pattern contributes to an observation. Good reconstruction suggests the model has captured meaningful structure, while poor reconstruction may indicate too few components or limited mini-batch data. Because mini-batch learning updates incrementally, reconstruction quality can vary early on, with common patterns usually captured more easily than rare ones. Mini-batch reconstruction should be judged by more than just low error. A model with slightly higher error can be better if its components are stable, interpretable, and useful for the analysis. In large datasets, this approach helps monitor learning efficiently while balancing accuracy with meaningful results. Python code. Mini-batch reconstruction. Mini-batches learn reusable components that can reconstruct the data. Scores combine these components to approximate each observation, and the reconstruction error indicates how well the original data structure is preserved. The script imports key tools for numerical computing, visualization, and machine learning. NumPy handles arrays and calculations, while Matplotlib creates plots. It also uses Scikit-Learn's mini-batch dictionary learning algorithm to learn components efficiently from data, along with a mean-squared error metric to measure reconstruction quality. The full Scikit-Learn library is imported, so its version can be checked later. The example begins by creating small synthetic documents for efficiency and clarity. A fixed random seed makes the results reproducible, and a simple topic word matrix represents 3 hidden topics across 6 word features. Each row shows how strongly different words belong to a topic, providing a controlled setup for demonstrating mini-batch reconstruction. The process simulates document word counts by first creating hidden topic weights for 60 documents across 3 topics using a gamma distribution. These weights are combined with the topic words matrix to form the basic document structure. Random normal noise is then added to mimic real data variation, and any negative word counts are clipped to 0, so the final values remain realistic. Before fitting the decomposition model, the code verifies that the word count matrix has 60 rows and 6 columns, meaning 60 documents described by 6 word features. If the dimensions are different, it raises an error because the data is not in the required format for the analysis. We build a mini-batch dictionary learning model from Scikit-Learn to find 3 underlying patterns in the data. It updates the model using small batches of 10 samples, which helps make learning efficient for larger datasets. The model can run for up to 200 iterations, and a fixed random state ensures the results are reproducible. The model is applied to the word count data to learn how strongly each component appears in each document, producing a set of component scores. These scores show each component's contribution to the documents. The model then uses the scores and learned components to approximate the original word counts, helping evaluate how well it captures the document's underlying structure. To evaluate reconstruction quality, we compare the original word counts with the reconstructed counts. The mean squared error shows how much information was lost, while the relative error measures the size of the difference compared with the size of the original data. Together, these metrics summarize how accurately the reconstruction preserves the original counts. The output checks the Scikit-Learn version and the data matrix size to support reproducibility and confirm the dataset dimensions. It then reports 2 reconstruction error measures, the mean squared error and a normalized relative error, both showing how well the model reconstructs the original data. Finally, it displays the rounded component scores for the first document, indicating how much each learned component contributes to that reconstruction. We label the 6 word features so they can be identified clearly in a plot. Then we create matching x-axis positions using NumPy's arrange function, which generates a sequence from 0 up to the number of labels. Finally, we choose a bar width of 0.38, so the bars are visible without overlapping too much. This visualization compares the original and reconstructed word counts for one synthetic document. A bar chart is created with the original counts shifted slightly left and the reconstructed counts shifted slightly right, so the 2 sets can be compared side by side. The plot includes a clear title, labeled axes, word feature labels along the x-axis, and a legend to distinguish the 2 data series. The layout is adjusted for readability before the chart is displayed. This script uses mini-batch dictionary learning to reconstruct synthetic documents created from topic word distributions with added noise. The model learns components from small batches and uses them to approximate the original word counts while reducing reconstruction error. It then reports mean squared error, relative error, and the first document's component scores, and compares the original and reconstructed word counts in a bar chart to show how well the method captures the underlying structure. LDA, topic reconstruction. Latent direct allocation, or LDA, represents documents as mixtures of topics, where each topic is a group of words that commonly appear together. Rather than reproducing exact text, it explains word patterns using a smaller set of topic components. This helps summarize large text collections by showing the main themes and how strongly each document reflects them. When interpreting LDA, look at both the topics and the document-level scores. A topic is understood through its most distinctive words, which reveal themes such as healthcare or finance. The document scores show how strongly each topic contributes to a document. So high scores point to central themes, while low scores suggest background content. When evaluating LDA, the goal is to balance statistical fit with interpretability. Too few topics can make themes too broad, while too many can create redundant or noisy fragments. Good topics should be coherent, stable, and suited to the analysis goal. The main question is whether LDA gives a meaningful, useful summary of the text, not whether it perfectly reconstructs every word. Python code, LDA topic reconstruction. This example shows how LDA topics can reconstruct documents by using topic mixtures to summarize word count patterns. The printed results compare the original word counts with the reconstructed counts. We import NumPy for numerical work and Scikit-Learn for machine learning tools. From Scikit-Learn, we use latent Dirichlet allocation for topic modeling and count vectorizer to turn text into token count data. Together, these tools prepare documents for discovering hidden topic patterns. We begin with a small set of short text documents, each focused on a theme such as sports, politics, or cooking. Because the documents are simple and topic-focused, they make it easier to see how latent Dirichlet allocation detects and reconstructs topics from word patterns. Scikit-Learn's count vectorizer converts a collection of documents into a numerical word count matrix. Each row represents a document, and each column represents a unique word from the full collection. Using the fit and transform step together builds this vocabulary and turns the text into numbers, making it ready for analysis, such as latent Dirichlet allocation topic modeling. Before fitting the decomposition model, the code verifies that the word count matrix has one row for each document. If the counts do not match, it raises an error, because the document-to-matrix transformation failed. This check helps prevent incorrect input from causing problems during model fitting. We use latent Dirichlet allocation, or LDA, to discover topics in a document collection and estimate how much each topic appears in each document. The model is set to find 3 topics, with a fixed random state for reproducible results. It uses batch learning on the full dataset and runs for up to 30 iterations to help the model converge. Latent Dirichlet allocation is used to learn topics from the word count matrix and convert each document into topic proportions. The fit and transform step does both tasks at once, producing a document topic matrix where each row is a document and each column shows how strongly that document relates to a topic. To reconstruct document word counts, first normalize each topic by converting its word counts into word probabilities. Then, combine each document's topic mixture with those topic word probabilities to estimate how often each word should appear in that document. Finally, scale the estimates by each document's total word count so the reconstructed counts match the original document sizes. The feature names from the vectorizer are converted into a NumPy array, so the words linked to each topic are easier to work with. The Scikit-Learn version is also printed to help confirm compatibility and interpret results consistently across different implementations. For each topic, we find the 4 words with the highest probabilities, since these best represent that topic. Their positions are matched back to the actual words from the vectorizer, then combined into a readable, comma-separated phrase. The result is printed with the topic number, giving a quick summary of the most important words for each topic. To compare a document with its LDA reconstruction, we first choose the first document. We then find its 5 most frequent words by sorting the word counts from highest to lowest. These top words let us compare the original counts with the model's reconstructed counts and judge how well the model represents the document's content. First, the topic mixture for the first document is printed, showing how the latent Dirichlet allocation model distributes that document across topics. Then, a comparison is prepared between the document's actual word counts and the model's reconstructed counts, helping assess how closely the model matches the observed data. For each important word in a document, we compare its actual count with the model's reconstructed count. The reconstructed value is rounded for readability, then printed alongside the word and its observed count. This gives a quick way to judge how closely the model reproduces the original word counts. Reconstruction error measures how well a topic model reproduces the original document word counts. It compares the original count matrix with the model's reconstructed counts and uses a linear algebra norm to measure the size of the difference. The final error, rounded to 2 decimal places, gives a simple indication of how accurately the model captures the document's word patterns. This script shows how latent Dirichlet allocation can model short documents as mixtures of topics. It converts documents into word counts, learns 3 topics, and estimates how strongly each topic appears in each document. It then reconstructs the original word counts from these topic mixtures and topic word probabilities, identifies the most representative words for each topic, and compares observed and reconstructed counts for one document. The final reconstruction error shows how well the learned topics explain the original documents. Interpreting components. Interpreting components in topic reconstruction means turning statistical patterns into meaningful themes. You look at the highest weight features, such as words or products, and infer what idea they share, like politics or consumer technology. This interpretation is a judgment, not a certainty, because components can reflect unexpected associations that require domain knowledge. Scores show how strongly each observation is connected to a component, helping link reconstructed topics to practical interpretation. In documents, they indicate how much a topic shapes the content, which lets analysts compare, group, and track themes over time. However, scores must be interpreted in context, considering both the component's meaning and the overall score pattern. Similar scores across many documents may suggest a broad theme, while a few unusually high scores may signal a niche issue or possible data artifact. Reconstruction quality shows how well a decomposition approximates the original data, but it should be weighed against clarity and usefulness. A highly accurate model may produce components that are difficult to interpret, while a simpler one may reveal clearer themes. In topic reconstruction, the goal is not only compression, but also understanding. So good interpretation checks whether patterns preserve the data structure, components are distinct, and scores match expectations. Python code. Interpreting components. This example shows how to interpret topic components in small documents. Words with high weights define each topic, while document scores indicate how strongly each document uses those topics. The setup imports the main tools needed for topic modeling. NumPy supports efficient numerical work, and Matplotlib is available for creating bar plot visualizations. Scikit-Learn provides non-negative matrix factorization to break a document word matrix into topics, while its count factorizer converts text documents into token count matrices. The code creates a small set of short documents with 2 clear themes. The first group uses political terms such as voting, elections, and campaigns, while the second group uses technology terms such as batteries, screens, and devices. This simple structure makes it easier to identify topics when applying topic modeling later. Count factorizer turns text documents into a numerical matrix, where each row is a document and each column is a vocabulary word. The fit transform method learns the vocabulary and records how often each word appears in each document. The vocabulary words are then saved as a NumPy array for easy access, creating a structured representation of the text for later analysis. Before decomposition, the code verifies that the word count matrix has 1 row for each document. If the counts do not match, it raises an error because every document must correspond to exactly 1 row. This check helps ensure the matrix has the consistent structure needed for the decomposition to run correctly. We create a non-negative matrix factorization model with 2 components to find 2 topics in the document word matrix. A smart initialization, fixed random state, and sufficient iteration limit help make the results stable and allow the model to converge. After fitting the model, the document scores show how strongly each document relates to each topic, while the learned components show the most important words for each topic. We approximate the original document word matrix by combining the document scores with the learned components. To evaluate the result, we compare this reconstruction with the original word count data in dense form. The reconstruction error is the size of the difference between the two matrices, and a smaller error means the model represents the data structure more accurately. The code reports the Scikit-Learn version to help confirm compatibility, then shows the reconstruction error for the non-negative matrix factorization model. This error indicates how closely the model approximates the original data, and rounding it makes the result easier to read. Together, these outputs help check the setup and evaluate the quality of the topic modeling. The process reviews each of the 2 topics found by the model and identifies the 5 most important words for each one. It does this by ranking the topic's word weights, selecting the highest weighted words, and matching them to their feature names. The words are combined into a readable, comma-separated list, then printed with a human-friendly topic number to show what defines each topic. A bar chart is created to compare how each document relates to 2 interpreted topics. The plot uses evenly spaced x-axis positions for the documents, then places the topic 1 bars slightly to the left and the topic 2 bars slightly to the right. Using the same bar width and clear labels makes the 2 topic scores easy to compare across documents. The plot is formatted to show document scores for interpreted components. It includes a clear title, labels the horizontal axis by document number, and labels the vertical axis by topic score. The document positions are matched with labels from D1 through D6, and a legend is added so the different topics can be distinguished. Finally, we use the Matplotlib show function to display the bar chart. This makes the document scores easier to interpret by showing how strongly each document relates to the 2 identified topics. This script uses non-negative matrix factorization to find topics in a small set of documents. It first turns the documents into word count data, then extracts 2 main topics based on the most important words. It also measures reconstruction error to judge model quality, and shows how strongly each document relates to each topic with a bar chart. In this lecture, you learned to apply dictionary learning, sparse coding, factor analysis, ICA and NMF methods, use mini-batch and topic modeling decompositions for larger or text-like data, and interpret components, scores, and reconstruction quality. In the next module, Module 25, we will go over manifold learning.
Thank you for your attention. See you all in the next lecture.